Hello again, AP Calc students. Mr. Record here from Avon High School. We're going to continue our talk about some of the Continental Mathematics League Calc Division questions from former exams, and we're going to look at the 2022 exam from the 21-22 season. So this is February of 2022, Meet 2, and this is problem number 8. It's a motion question with a little bit of a wrinkle to it. So let's read this together. It says a train is just starting to move out of a station with a constant acceleration of 3/4 yards per second squared. At this time, a man a certain distance d from the nearest entry door of the train is running at a constant speed of 3 yards per second. We want to know what is the greatest distance d that could be where the man could still catch the train. And so I'm going to start by drawing a picture here. It will be a bit of a crude sketch, so bear with me. So let's kind of make this train sort of like a bullet train here, just with one car. And for the sake of simplicity, I'm going to put the door at the very end of the train. And we have to think about this train as sort of moving just with one single point, right? It's the same as just this single green point that's moving to make things just a little bit easier so that we can use our particle motion relationships. And then, of course, the train is running, of course, along some kind of a track. We're not going to have this person necessarily running behind the train on the track, but let's say that they're running along the side there, the platform, if you will, so that they are almost even with the side of the train so that they could just easily dive in if they wanted. So we got the man. I guess it could be a woman, right? So here's that person running, hopefully trying to catch that train. Now, one of the things that we're going to want to think about here is a sort of a scale, if you will, an x-axis that will really depict, where we are positioned in this particular problem. And to make things kind of simple, I'm going to choose to let this point be along our x-axis to be at position 0. So therefore, this man or person is to the left side of the vertical axis, if we really needed to call that the y. We really don't. And the train would be at the end of the train, at least right at that origin. Now, what I'm going to have us do is just start to list all sorts of relationships that we know about both the train and the man. So we have all of this information that we could find, right? We know how to find acceleration, or at least it was given. We're going to have some information about velocity, and we're going to have to use information about position. And if you remember, if you're working kind of going the other direction, you would just take derivatives of each of these. Derivative of position is velocity, derivative of velocity is acceleration. But if we're working the opposite direction, we're going to be doing integrals, right? And right off the bat, this problem says that the train has a constant acceleration of 3/4. And so from there, we should be able to find the velocity quite easy. So I'm going to call this a sub t, right? Acceleration of the train. So the velocity of the train would just be the integration of this 3/4 with respect to t. And that, of course, is going to give us 3/4 t. Now, it's also going to give us a constant, right? I mean, technically, we do need to add a plus c to this. However, by virtue of the language in the problem, I'm seeing here that it says the train is just starting to move, which indicates to me that the train was stopped, and therefore the velocity of the train at time 0 would be the c value, and that velocity we just said is going to be 0 if the train is stopped. So we really don't need that plus c because the value is 0. I'm going to move this position down a little bit to give us some room to work. And now we're going to do the same thing in order to find the position of the train, which I'm going to use S capital T, S subscript T. And we know that that is going to be the integration of the velocity with respect to t. And if we perform this integration, we would get 3/4 t squared over 2, or 3/8 t squared. And once again, we would need a plus c, technically. But as I said before, by using the idea that the back of the train is position 0, it means that the position of the train at time 0 is 0, and we get another plus c that's going to be 0. Now, there's other ways that this problem could be set up. It is not entirely out of the question that you let the man be at position 0, which means you're going to have a constant here of likely a plus d. If you think that that's easier, that would certainly work out. But if we're going to put the 0 here, I'm going to make sure that this man has a position that's going to be at minus d. That's going to come out to be really powerful, very important information as we continue to work through this problem. Okay? Now, when we go to the man, we're going to do the same thing. We're going to try to find as many of these relationships as we can, but unfortunately, we're not going to have much luck trying to find the man's acceleration because, well, it's not that we can't find it, it's just that we're not going to need it. The first information that we have about the man is that he's running at a constant speed of 3. So that's going to be the velocity of the man. All right, and I don't want you to get confused with speed and velocity. Speed is the absolute value of velocity. And since we're already running in the rightmost direction here, we're going to go ahead and consider the velocity to have a positive sign. Now, if you needed it, the acceleration of the man is 0, right? Because he's running at a constant speed, but I don't think the acceleration is going to be what we're looking for, right? We're going to be looking for the speed of the man, which means we have to integrate 3 with respect to time. And that, of course, is going to give us 3t plus some constant, right? So let me slide this over so I can say the position of the man is going to be 3t plus some constant. But remember, we said that at time 0, the position of the man is going to be this negative d because he's to the left of that particular 0 value. And so now we have our two position expressions here. Position of the train, position of the man. Well, the only way that this man can get through that door is if his position and the train's position were equivalent, right? That's what we're hoping for there. And so we're going to go ahead and take those two values that we've just computed, the position of the train at time t and the position of the man at time t, and we're going to set those equivalent to one another. Now, there's still a few more things that we have to do here, and namely, this problem is a little tricky because of the fact that we have two variables, and I want to talk just a little bit more. It's going to be very important that we are able to work with this particular equation. And the thing that I'm going to suggest is that we move all of the terms over to one side. And so that means we're going to subtract a 3t, we're going to add a d, and this is going to be equal to 0, of course. And it's this thing here that I think we're going to start to become really interested in. That's a really interesting expression that if we know a t value, it will produce a d value that starts to become kind of interesting for us. Now, in order to work with this a little bit easier, let's multiply through by an 8, because it just makes this equation a little bit easier to work with. And as I said before, this part here is what I really want to figure out what's happening with, because if we want this to have this idea of a greatest distance, it's kind of like when you have a function that we're trying to find its greatest value, its maximum, we know that we have to take that function and compute its derivative. And then we would set that derivative equal to 0, okay? And so I'm going to go ahead and declare this to be a distance expression, okay? I just don't want to call it d equal because I don't want it to be confused with the d that's already involved in that expression. So if we're going to try to find that maximum, let's take the derivative of this distance equation with respect to t, and that of course is going to give us 6t minus 24. Okay? Now, I'm going to probably close out the video here and just give you a little bit of advice about what to do next. You know that in order to find a critical value, you would set this derivative equal to 0, and you're going to get a very nice t value. You're going to get a very nice integer value for seconds. Now, that integer value we get is our only t that's a critical value, and it will be the t when we have this greatest distance d that the man can still catch the train. And so in order to find out what that d is, you'll need to go to an expression, an equation, that will allow for that t to be used. And there's no better place than to go here, or if you don't want to use the fraction coefficients, you can go right back to here. Either one, when you use that value of t, is going to give you a d once you solve that equation. And that d is also going to be a very nice integer value in yards. And that will be that d that the man would have to be standing at no more than in order to have any chance of catching up to that train. Anyway, hope this one helps a little bit, and we'll see you at the next video.